The future of communication security will probably make use of quantum physics. The main interest for the emergent technologies of quantum communications is due to their resilience, at least in theory, to a range of quantum attacks that hackers could perform on today's security systems. Such a security advantage relies on the fact that quantum states cannot be cloned, contrary to the traditional carriers of information, such as the bits in our computer. The theoretical principles are quite clear to experts, but now it's time to actually make this technology work. With this goal in mind, the researchers of QCALL, thanks to the coordination of a group of universities and companies across Europe, set out to solve some of the implementation challenges that quantum communications faces today. The basic element of our communication will be light quanta, also known as photons. Light is already used in optical fibers for internet connections, and it has the potential to carry quantum information. Now that we chose our information medium, we need to find a communication protocol that works. In short, you can think of a protocol as a set of rules that define how the communication will be carried out in order to prevent hackers from stealing information. The most important thing for a communication protocol is, well, that it's actually secure and reliable. Proving that a protocol is secure involves lots of math and knowledge of the devices that will be used for the communication. Davide at the University of Geneva and Shovik at the Sorbonne University in Paris focused exactly on this task for different protocols. Davide worked on protocols with few photons sent along the communication link one by one or in packets, while Shovik explored protocols with continuous streams of light. Both of these approaches are promising and have their own strengths and weaknesses. There are also some hybrid approaches, some of which were explored by Nilesh at Paritech. Quantum communication protocols can also involve multiple network users, not just pairs. Indeed, thanks to the quantum entanglement of the distributed photons, each user obtains the same outcome when measuring their photon. These outcomes can then form a shared encryption key. Federico at the University of Düsseldorf worked on the subject, showing some ways in which more than two network users can safely share encrypted messages among themselves. Even after a protocol has been proved to be secure in theory, the imperfections of the devices implementing it can reduce its performance. For instance, the light sources that generate the photons, or the repeaters that help joining links to extend the communication distance, or the light detectors used as receivers, all have some specific properties that must be taken into account by the security proof. Robert at the University of Vigo was able to show how a popular protocol was quite slower than expected once you consider all the imperfections in an actual implementation. Guillermo at the University of Leeds and Margarida at the University of Vigo also considered various kinds of imperfections and limitations of the devices, and were able to devise protocols that are optimized for the task. Liu Meng at the University of Leeds worked instead on optimizing the resources required by communication protocols that make use of many channels at the same time. These were just few examples of the topics our team worked on. Jump to our next video to see the experimental implementation of the technology involved, or to our first video to have a brief introduction on quantum communications and cryptography.